This is an image taken by NASA's Cassini spacecraft. Who can tell me what planet this is? It's okay, shout it out. Saturn. That's right. Saturn is in this picture. It's kind of hard to miss. But there's something else. We are in this picture. If you are more than 10 years old, you are in this picture. Carl Sagan once said, "That's here. That's home. That's us." This image was taken in September 2006. This is another image from Cassini, taken in July 2013, as before Saturn and its rings loom large. But if you are more than 2 years old, you are in this picture. Sagan was referring to this image, the original pale blue dot. It was taken by Voyager 1 on February 14, 1990, over 26 years ago. It was after Voyager had passed beyond the orbit of Neptune and was looking back at the inner solar system. Sagan poetically called this a mote of dust suspended in a sunbeam. Consider that mote of dust. That is our entire planet. So what do you know about it? Zooming in, this is that planet that you can barely see in those faraway images. Think about what you can see here. What do you know from looking at this planet? It has water, lakes, it has oceans. It has land and mountains. It has clouds and wind and weather. It has vegetation. If you had something called a spectrograph, which could analyze the light in finer detail, you might detect water vapor, carbon dioxide, methane. These are the signs of life. All of this information is encoded in the light of our sun reflecting off of our planet. And this leads me to a big question. It's maybe the biggest question that any of us have ever asked. Is our planet, our Earth, our home, the only one like it in the universe? Now, it turns out that we live in a remarkable time in human history, because for the first time, we are on the verge of being able to answer this question. So let me tell you what we know. Very recently, astronomers have begun to detect and study planets orbiting distant stars. These planets that orbit stars other than our sun are called extrasolar planets, or exoplanets. Any planet orbiting its star, whether an extrasolar planet or the Earth itself, has an effect on that star. It tugs on the star through gravity, causing the star to wobble, just moving. And if it passes between us and the star blinks. It gets fainter for a brief moment. We can measure the wobble by measuring the Doppler shift of the star's spectrum. When the star moves towards us, it is blue shifted, and as it moves away from us, it is red shifted. This is conceptually similar to how the sound of a train whistle gets higher than lower as it passes, only this is happening with light. So we just measure the amount of Doppler shift, and that tells us the planet is there, and it also tells us something about its mass. And when a planet passes in front of its star, the star gets fainter. Astronomers call this a transit. The amount by which the star gets fainter tells us the radius of the planet, its size. And this method, especially because of NASA's Kepler satellite, has discovered thousands of exoplanets. So because of such remarkable techniques, we now know a truly amazing fact. On average, for every star in our galaxy, there is at least one planet. And you should know that I'm quoting a slightly older result just to be safe. In reality, we are now very sure that the number is higher than this. So everyone take a moment and appreciate this image of our galaxy, the Milky Way. If you count the number of stars that you can see, you are counting the minimum number of planets that you cannot see. Our galaxy is loaded with planets. And this is something we've only known for just a couple of years. But are any of those planets like this one, the planet you and I call home? What do we know about these planets? Almost nothing. These observational techniques, that is the way we detected those planets, are all very indirect. With few exceptions, we found those planets by measuring their effect on the star. We did not actually capture light from the planet itself. The Doppler technique, where we measure the wobble, gives us just a lower limit on the planet's mass. And the transit technique, the decrease in star brightness, tells us the radius. Both of them let us measure the period of the planet's orbit, the year of that planet, from how often the signal repeats. And this tells us the planet's distance from its star, which just gives us a hint about its temperature. But that's it. These indirect techniques tell us nothing about the planet's atmosphere or its surface. We don't know if they have water or if they have clouds. To gather this information, we have to capture light from the planet itself. And this is very, very, very hard. This is an image of the star Beta Pictoris. It's a star you have to be fairly far south to see. That's why we go to Chile. One of the reasons we go to Chile. It's relatively close to us. It's about 63 light years away, which is why it's so bright compared to the other stars in this image, even though with your naked eyes it would be pretty faint. So let's zoom in. Now it looks pretty bright, doesn't it? Its light is also spread out into kind of a blob. This is because of turbulence in the Earth's atmosphere. This is what happens when stars twinkle. So now imagine plucking a hair from your head and holding it at arm's length. The angle that your hair would cover is roughly 1/2 of arc across. That's 1/3600th of a degree. It's a tiny angle. This red circle is 1 arc second across. At the distance of this star, Beta Pictoris, this circle reaches out to about 10 times the distance of the Earth from the sun, or roughly the distance of Saturn from the sun. So if we want to image planets like those in our solar system, we have to be able to zoom in on this circle, which is no wider than one of your hairs held at arm's length. If we do this, this is what we see. The faint white speck is the extrasolar planet Beta Pictoris b. It's so faint I'll draw a circle around it for you. This is a false color image taken in an infrared wavelength, or color of light. It's just a little longer than you can see with your eyes. This planet is 100,000 times fainter than its star, and it's closer to that star than the width of one of your hairs held at arm's length. Now, I didn't discover this planet, but I did take this image with the instrument I helped build for the Magellan telescope in Chile. The telescope is 6.5 meters, or 21 feet across. Our instrument is specially designed to correct the turbulent twinkling of stars and zoom in so that we can see planets like this. This is another planet imaged with our system in Chile. You can see this planet, which we very creatively called HD 106906b, in the upper right corner. And from an astrophysics perspective, it's very interesting, in part because it is so far from its star. And if you are not from Brookings, South Dakota, you might not have heard of this planet. But those of you here in Brookings today should be very familiar with it. Because I think the truly important fact about this particular planet is that it was discovered by a Brookings bobcat. A graduate of Brookings High School, whom you might know as Vanessa Cheeseborough, now Vanessa Bailey, discovered an entire planet orbiting a star 300 light years away. Here's Vanessa and me standing next to our instrument, the Magellan Adaptive Optics System, or MagAO in Chile. And Vanessa used MagAO to make her discovery. And this picture was taken just 2 nights after she had taken her images. Though at the time we didn't know that she had discovered the planet yet. So these are 2 examples where we have imaged, or where we have collected light from an extrasolar planet. But these are not just nice pictures. These are actual scientific measurements. We can take many such measurements, shown by the points on these plots, and compare them to theoretical models, shown by the solid lines. And to an astrophysicist, these graphs tell us about the temperatures on these planets, and are even revealing details such as how cloudy they are. So we are studying the conditions on planets tens and hundreds of light years away from Earth. And this is what you can do when you collect light from a planet. And of course, these are not the only images of exoplanets taken to date. These are 3 other prominent examples. Depending on how you count and who you talk to, we have imaged a little more than 10 planets orbiting distant stars. And you should know that these planets are nothing like Earth. They are far larger and much hotter. So out of the several thousand known exoplanets, we have images of about 10. That's it. It's just a tiny fraction. Imaging and characterizing exoplanets is really, really hard. And we are just learning how to do this. This is a rendering of the plans for the giant Magellan telescope. This is a huge telescope being built right now by a large consortium of engineers and astronomers from universities and observatories around the world. It's actually going up on the next mountain peak over from where Vanessa and I took those pictures. When we finish it in the middle of the next decade, it will be 25 meters or 82 feet across. And it will be a revolutionary new instrument, allowing us to image exoplanets in far larger numbers and closer to their stars than we ever have before. And it's going to enable us to begin imaging Earth-sized planets. And this is an illustration of one of several concepts for a future space telescope, which could be as big as 12 meters or 39 feet across. Free from the Earth's atmosphere, a space telescope such as this could image exoplanets just like Earth around stars just like our sun. It has been just over 20 years since exoplanets were confirmed to exist, and just a few years since we understood that they were extremely common around stars in our galaxy. In the next 20 years, telescopes like these will finally take an image like this, a pale blue dot, but one orbiting a distant star, a mote of dust suspended in a star beam. Such images aren't going to be as pretty as this one, but they will contain all of that information that you know from looking at this picture of our home. And those images will answer this big question: is this the only one? Thank you.